This problem is an application of Bernoulli's equation. Let me start by reading the statement of the question. Water is flowing at 10 gallons per minute from a standard 1-inch Schedule 40 steel pipe into a standard 2-inch Schedule 40 steel pipe. The pipes are horizontal. Calculate the pressure difference in PSI between the two pipes. So we have two horizontal pipes. We have a 1-inch pipe, which I'm going to draw here. This is a 1-inch Schedule 40, and the 1-inch is a nominal dimension or a nominal size, and if you look it up in the table, link is below, the diameter of this 1-inch pipe is 1.049 inches. And the fluid, or in this case the fluid is water, is flowing at a volume flow rate Q of 10 gallons per minute. And we're told that this water then flows from the 1-inch pipe into a 2-inch pipe, and presumably this happens through some type of gradual enlargement, but it doesn't have to be. There could actually be anything happening in between, but the only thing that we're assuming is that there are no frictional losses during that enlargement. And we flow into a nominal 2-inch pipe, which has an inside diameter D2 of 2.067 inches. Now the continuity equation tells us that if we have 10 gallons per minute entering from the left, mass is conserved. The only other place that the fluid can go is exiting at the right, and we have 10 gallons per minute exiting on the right as such. So what's going on in this problem? Well, the fluid starts off with a certain velocity in the first pipe. So let's choose a point, and we're actually going to choose 2 points. The first point we're going to choose is this one here. We're going to call this point 1 in the 1-inch pipe. And we're going to choose another point here, point 2 in the 2-inch pipe. And at point 1, the fluid has a velocity v1. And at point 2, the fluid has a velocity v2. At point 2, the fluid has a pressure P2. At point 1, it has a pressure P1. Both these points are at the same elevation because the pipe system is horizontal. So we have that the elevation of Z1 equals the elevation at Z2. Now, if we know that the volume flow rate Q is 10 gallons per minute, we know that Q in the first pipe has to be the cross-sectional area of the first pipe, A1, times the velocity of the flow in the first pipe, V1. This has to equal the cross-sectional area of the second pipe, A2, times the velocity of flow, V2, in the second pipe. I can now rearrange this expression and solve for V2. And when I solve for V2, I find that V2 equals the ratio of A1 over A2 times V1. Now this ratio of the area 1 over the area of 2, that's equal to the diameter 1 squared over the diameter of the second pipe squared. And when you work this out, it works out to be about 1/4. Again, it's a 1-inch going to a 2-inch pipe. The ratio of the diameters is 1 over 2. The ratio of the areas would therefore be 1 over 4. And when you use the exact dimensions, you actually get that the ratio in this case is 0.26. So what we find from the continuity equation is that the velocity at point 2 equals 0.26 times the velocity of point 1. So the velocity at point 2 is about a factor of 4 smaller than the velocity at point 1. And that we arrived at that result just by using the statement of the continuity equation. Now, what we're trying to find is the pressure difference between the two pipes. And the pressure in the fluid is a form of potential energy. And essentially what's going on here is that we see that the velocity drops by about a factor of 4. If the velocity is decreasing as you go from one pipe to the other, that means the kinetic energy of the fluid in the pipes must be decreasing. However, we know that energy is conserved. So if that kinetic energy is decreasing, there must be another form of energy which is increasing. Since the pipes are horizontal, it's not going to be an increase in gravitational potential energy, so it's going to be an increase in pressure energy. So what we see is that the kinetic energy decreases as we go from 1 to 2. However, the pressure energy increases as we go from 1 to 2. In other words, we know that V2 is less than V1, and therefore P2 is going to be greater than P1. The pressure in pipe 2 will be larger than the pressure in pipe 1. Now, in order to quantify this and actually determine how much larger that pressure is, we need to apply Bernoulli's equation, which is just the statement of conservation of energy for a steady flowing fluid without energy losses. And of course, it's also incompressible. So let's write down Bernoulli's equation between point 1 and point 2. We have P1 over gamma plus Z1 plus the velocity head, V1 squared over 2G, and that has to equal the total energy at point 2, P2 over gamma, plus the elevation at 2, Z2, plus the velocity head, V2 squared over 2G. Now, there's some simplifications that we could do right off the bat. We already stated that Z1 equals to Z2. That means they'll cancel on both sides of the equations. And I want to solve for the pressure difference. And in order to do that, I'm going to bring this term, this P2 over gamma, I'm going to subtract it from both sides and bring it over to the left. And then I'm going to subtract the velocity head at 1 from both sides, which would bring it over to the right. So that rearranges this expression as follows. I have that P1 over gamma minus P2 over gamma equals V2 squared over 2G minus V1 squared over 2G. I'm now going to multiply both sides of this equation by a factor of gamma, and I'm left with P1 minus P2 equals gamma over 2G V2 squared minus V1 squared. And this final form of Bernoulli's equation is what I'm going to need to solve for the pressure difference between the two pipes. So let me put a box around this so we don't forget about this. So rho, like we said, Greek letter rho is the density. That's just the density of water in this case. That's something that we can look up or we might have memorized. But we need each of these velocities. But the problem doesn't give us the velocity, it gave us the volume flow rate. So how do we find the velocities in each of these pipes? So let's start with pipe 1. We know that the volume flow rate Q is equal to the cross-sectional area of pipe 1 times the velocity in pipe 1. We can rearrange this to find that the velocity in pipe 1 is equal to the ratio Q divided by A1. Q was 10 gallons per minute, and area A1 could either be solved for from the diameter or looked up in the table. I just took it from the table. Area 1 is 0.006002 feet squared. And you'll notice that we don't have a consistent set of units. In order to get this into a consistent set of units, we need to multiply this by a conversion factor. And the conversion factor that I'm going to use here is that there is 1 foot cube per second in 449 gallons per minute. And if you remember, this conversion factor, this factor that's in parentheses, is just equivalent to 1. So it's a factor that just allows you to change between different sets of units. And you'll notice that GPM cancels with GPM. The foot squared in the denominator cancels with 2 powers of feet in the numerator. And we are left with units or dimensions of foot per second, which is a velocity. So when you work this all out, I take the numerics, 10 divided by 0.006002 divided by 449. I find that my velocity in the 1-inch pipe at point 1 is 3.71 feet per second. Now, we could solve for the velocity of 2 in the same fashion. We could just use that V2 equals Q over A2, but we already know from earlier on, and let me scroll up, when we use the continuity equation, and let me put a box around it again, that V2 is 0.26 times V1. So I can just use that same expression, that V2 is 0.26 times V1. And I therefore find that that V2 is equal to 0.965 feet per second. So now I have everything I need. I have all the values I need to go back and plug into Bernoulli's equation to solve for the pressure difference. I have velocity of 1, I just calculated. The velocity at point 2, I calculated here. The density of water, rho, let me just write that down. You can look at it in the table, but rho is 1.94 slugs per foot cubed. So now let's plug in these values and make sure that we get a pressure with consistent or the correct unit. So I have P1 minus P2 equals rho over 2. So I have 1.94 over 2 slugs per foot cubed times V2 squared minus V1 squared. So that's times 0.965 feet per second squared minus V1 squared, which is 3.71 feet per second quantity squared. So 1.94 over 2 is 0.97. So I have 0.97 slugs per foot cubed times 0.965 squared minus 3.71 squared. This works out to be negative 12.83 feet squared per second squared. And the minus sign is not a problem. It just tells us the pressure at 2 is larger than the pressure at 1. That is, that P1 minus P2 will be negative. And that's something that we already argued would be the case earlier on. So let's rewrite this. We have P1 minus P2 equals minus 0.97 times 12.83. It's minus 12.45. And we're left with slugs per foot cubed times foot squared per second squared. Okay, that doesn't look like a pressure. So we need a pressure. We want pounds, we want inches, we want PSI, pounds per inch squared. Where is all that hidden in this mess of units? Well, I think the slug is a trickier one. And if you forgot how to convert from slugs to pound, let me just make a little side remark here. This is just a little side statement. Just remember Newton's law, F equals ma. Force would have dimensions of pounds. Mass would have dimensions of slugs. Acceleration has dimensions of foot per second squared. So we see that 1 pound is a slug foot per second squared. Let's go back here and just rewrite this as a slug times a foot per second squared. And then we're left with 1 over foot squared. Check that that works out. This part here is just equal to a pound. So we're left with a pound per foot squared. So we're left with P1 minus P2 equals minus 12.45 pounds per foot squared. This equals minus 12.45 PSF, pounds per square foot. There's nothing fundamentally wrong with those sets of units, but we want to convert this to PSI. The question had it in terms of PSI. So how do you convert this into psi? Well, you start with the number negative 12.45 pounds per foot squared, and you multiply this by a conversion factor that 1 foot has 12 inches, and we need to square this. And it's only after we square this that the foot squared down here cancels with the foot squared up there. And we are therefore left with that P1 minus P2 equals negative 0.086 pounds per inch squared. And if you like, you could rearrange this and write this that P2 minus P1 equals 0.086 psi. So that's our final answer. So the pressure at 2 is larger than the pressure at 1 by 0.086 psi.